Hello and welcome to section 4.1, Antiderivatives and the Indefinite Integration. Basically what we're going to do in this is we're going to reverse the process of differentiation. That's why this is called antiderivatives. Well, normally when we took the derivative of x squared, we got 2x. No big deal, something we're used to. Now we're going to go backwards, and I'm going to give you the function is 2x. But when we go backwards, we get x squared plus c. And now where does this constant come from? Well, think about it. I told you in this first one that the x-axis, the x-intercept, was 0 because I didn't add or subtract anything. But if I was to take the derivative of something like, we'll say g of x equals x squared plus 4, well, if I take the derivative of that, I get my 2x. And the 4 goes away. So when I go backwards, I have to keep into account that there could be some other number besides the y-intercept, besides 0, 0, that this thing's going through. So I need to make sure of that, and that's what we get. That's where our constant of integration comes from. So we need to know that's what we're dealing with when we're talking about this, that there's going to be a constant when we do the antiderivative, because we don't know if there was a number there, a constant that went away. So we got to keep track of this. What this gives us is a family of functions when we do the antiderivative. Because if I do x squared plus c, think about it, there's a whole bunch of U-shaped graphs that I would get that, depending on where c is, what c is, to what the solution is, what the actual solution is. And we'll talk about how we get the c value later, an actual number later. But right now we're talking about a family of functions, because this x squared could cross the x-axis at any given point. So g prime of x equals 2x is what we call a differential equation. Basically, if we have a prime equal to some equation, that's a differential equation also. And so differential equations in x and y is an equation that involves x and y and the derivative of y. So like y prime. So down here you'll look, there's two examples of differential equations, and we're going to use those as we go along. So our first example is I gave you this differential equation of y prime equals 2. So now basically this is telling me the slope of my original equation is 2 everywhere. Slope equals 2 everywhere. And so if that's the case, then if I was to do the antiderivative, I have to think, well, what did I differentiate to get 2? Well, that should have been 2x. But does it necessarily cross at 0, 0, cross my y-intercept be 0? Well, the answer to that is no. It could be any value. It could cross the x-axis. And if I was to take the derivative of this, say I make c negative 13, then I could get something like y equals 2x minus 13, and if I take the derivative of that, I will get 2. So it just depends on what that c value is. I just made up this negative 13. It could have been 4, could have been 17, it could have been any number, but this is where this constant of integration comes from. So this is the general solution, because we need more information in order to find out where it actually crosses the x-axis. But when they ask for a general solution, they're asking for a blanket constant of integration of c. So then we have notation, new notation for antiderivatives. And so we had our original equation, what we're used to, is dy dx equals f of x. Well, then we talked about differentials, that dy equals f of x dx. Now, these differentials help us out because when we do our antiderivative, this little dx becomes kind of important for what we're doing. Because it becomes what we're integrating to, what we're dealing with respect to. So we're trying to find out with respect to x. So we have antidifferentiation, indefinite integration, and the integral sign. All of these are kind of new terms, and this is the integral sign. It is like a little curvy s. So then this f of x basically is our variable of integration, what we're dealing with, or our integrand. Sorry, I said that wrong. This is our integrand. And that's integrand. And then this is our variable of integration, what we're differentiating towards, x. We're going to be changing powers of x's. Variable of integration. Probably recognize the c there as our constant of integration. And the only way to get rid of a constant is to have an initial condition, and then this was the antiderivative. The antiderivative of little f of x. So in this case, we're taking this basically reads here, this right here, will read as the antiderivative of f with respect to x. And so the integral is a synonym for antiderivative. They kind of go back and forth. It just depends on what they're trying to get from you on the AP test and what we're asking for on our tests. So then we have our basic rules, and all of these rules apply. They're in our book on page 250. Make sure you get these down. You don't need to copy them down because you have it in your book. You might want to flag the page that you have it on, but you need to know these, and we're going to be using them, and we'll be adding on to these as we go. I mean, we're going to be using these basic ones. You don't need to understand them all right now. Probably the basic ones would be the first few, but we'll talk more about those and have a chance to practice them in class. So then we lead into initial conditions and particular solutions. So if we were to take the antiderivative of something or the integral of something, we get a family of functions. We talked about that. That's where the constant comes up. So I give you this function down here. I'm asking you to do the integral of 3x squared minus 1 dx with respect to x. When I do the antiderivative, I get y equals x cubed minus x plus c. So let's just do this real quick. Let's talk about it. So I've got 3x squared minus 1, and I'm going to take that with respect to x. So if I raise this up a power, that means x will go to a cube, and then I have this 3 here that I need to get rid of because I put it up front, because I multiplied by the 3. So that would mean that the 3 that was originally there gets divided by the new power. Over here, I have the negative 1, and the x is to the 0 power that's originally hidden there, because there's an x to the 0 power, because that's 1. When I raise that up by a power and divide by that new power, there's my new x term. And then don't forget that you got to add on your constant. So this thing simplifies to that y equals x cubed minus x plus c. Now that's our general solution. It could be any one of these graphs over here. Any one of them, because we don't know what c is. The only way we're going to know what c is if they were to tell me that this function actually goes through a particular point. And so they'll have to tell you to give you the information to get a particular solution. And they'll just ask you for the solution. They'll say given the initial condition, but you need to be looking for initial conditions, particular solution as a term. And so then if they tell you that, then you should be able to find out what c is. And so I gave you the point 2, 4 as the curve passes through this point, so that would be considered an initial condition. By plugging in y is 4 and x is 2, I simplified down to find out that c came out to be negative 2. So this guy right down here came out to be my particular solution for this function. It's the actual solution that I get, because I'd basically be saying 4 equals 2 cubed minus 2 plus c, which gives me 4 equals 6 plus c, and then negative 2 equals c. So that's where that came from. And so all of this is just a matter of us trying to find specific ones. So that would have been, if you look back at my graph, this guy right here, it would have been crossing at negative 2, the darker graph of them for our particular solution, because it depended on what point we went through. So then here's another example of it. And so we're dealing with f prime of x equaling 1 over x squared. And it's got to be greater than 0 because we can't have a negative square root, blah, 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 so on and so forth. And it's got to go through the point, it looks like 1, 0. So that's our initial condition, so that's where we're looking for a particular solution. So if I want to find f of x, remember that's the antiderivative of this, and I'm going to rewrite this as x to the negative 2 dx just to save myself a step. And so then remember that when we're doing an antiderivative, we're going the opposite direction. So we're raising this thing up a power, so it becomes x to the negative 1, and I'm going to divide by that new power. Because watch what happens when I take the derivative of this f of x. And so then and then don't forget that I have to add on my constant. So this f of x is our new equation that we get negative x to the negative 1 plus c. So let's just check it to make sure that we have the right f of x. If I take my derivative of this function, I multiply by my negative 1, which means I have negative, which was there first, times negative 1x, and reduce it by a power, and then my constant goes away, so I'm left with x to the negative 2, which is what I started with. So this right here is my general solution. That's the solution I would get if I didn't know any other points. This is where my family of functions comes from. So now if I plug in my y is 0 and my x is 1, I can find exactly where it crosses. So that's what I'm going to do. Y is 0, x is 1 to the negative 1 power plus c. Well, 1 to the negative 1 power is still 1, so 0 equals negative 1 plus c, so that means c has to be 1. So my particular solution, the overall final solution to this problem, is that f of x equals 1 over x, negative 1 over x, plus 1. And that's really what I was looking for when I'm doing this problem. Now, if you don't quite understand, you don't feel comfortable with this antiderivative stuff yet, don't worry. We will come to class prepared to ask your questions. We will talk more about it in class, and I promise you you'll get plenty of practice from this as we go along.